Hi, I'm Ben-Yaakov. This presentation is entitled To Ferrite Bead or Not to Ferrite Bead in Power Electronics. I'd like to thank Frenetic company for sponsoring this video. They are also very kind to offer a free trial to the viewer of this video. The details are given in the description section of this video. Now, the presentation of this video is not related to products of Frenetic. Ferrite bead can be useful in power electronics as part of a filtering system. I'm showing here a source, and then I have here a load, which is another power supply. This could also be a power supply. And then the ferrite bead is supposed to, first of all, filter out a ripple that might be here at the source from coming into this part here, and then also to help to sort of lock the ripple generated by this unit, which we would like it to go through this decoupling capacitor from penetrating into the source. So the bead is useful here, or could be useful here, as a filter in actually both directions. Now, why a ferrite bead and not just an inductor? The reason is, the common knowledge says that a ferrite bead has a resistive part, which is also helping to damp oscillation that might start if you have just a inductor. So here you have a resistive part, which we are going to talk about. So ferrite bead is assumed to be a better choice. Now let's have a look at some of the basic parameters of a commercial ferrite bead. Here is the impedance. I'm going to talk about it a little bit later, so let's not dwell into it now. But here it says that the rated current is 1.6 amp, which is fairly nice. It's a high current bead. And then the DC resistance is 0.12. It's compatible with this current, of course. You cannot have a DC resistance large if you have that higher current. Now the impedance at 100 megahertz, this is the red one, is the impedance at 100 megahertz. It's sort of like 1 kilo ohm, 1000 ohm. That's what it says here. Now the tolerance is 25%, which is not too bad. And this is the size. It's not a very small unit. Well, it's not that large, but it's sort of a medium-sized SMT device. So let's have a look now at the plot here. Now we see, first of all, the total impedance, which is the red one, but the impedance is composed of actually a number of parts. Showing here actually the resistance or resistive part and the inductive part. The light blue is the resistive part. You see at the very beginning there is almost no resistive part, and then it goes up. Now this resistive part is not a DC resistance, it's an AC resistance. You can think about it like a loss of a ferrite material. Okay, it's a loss due to the AC, it's not affecting the DC. And of course, being a loss, then it starts to be significant at high frequency. At low frequency, up to say 10 megahertz, the resistive part is relatively small. On the other hand, there is an inductive part, which is the green one. This is the impedance of this inductive part. At the beginning, the total impedance is due to the inductive part. Here it is. And then this inductive part drops because the permeability actually of the material drops at this high frequency. And we are left with the losses, which are the resistive part, until we come to this peak here, and then there is a drop. Well, the drop is actually due to two phenomena. One is the capacitance of the unit, which then shorts the unit. And then there is also a change in the so-called imaginary permeability, which is also causing a drop. But this part here is very high frequency, is really not relevant to power electronics at all. For filtering of very high frequency, the ferrite bead is excellent. It's very, very good. If you are talking about hundreds of megahertz, this is a very good choice. But we are now concentrating on the lower frequency, which is relevant to ripple in power electronics. And this will be like a couple of, say, 20 or 10 megahertz, not beyond that. That's not of interest when you're talking about ripple in power electronics. So how much is this inductance for this particular unit? So I'm picking up one point here that's 200 ohm at 6 megahertz, and this is omega L, and therefore the inductance is 5 microhenry. And then we have the DC resistance of 0.12. Obviously, later on, we're going to have an AC resistance, but at this region here, the inductive impedance is much larger than the resistive impedance. And now I'm going to present a real case that we have encountered. And I'm going to do, first of all, some simulation and then show you some experimental results. So what we have here is a source. This is actually a power supply by itself. And then we have a output capacitance of this source, which we don't know actually what is the value of. And then we have our unit here. And here we have a decoupling capacitor of 3 microfarad. And it was thought that it'll be nice to have here a ferrite bead. This is the ferrite bead I was talking about, which means that it is like something like 5 microhenry inductance at this switching frequency. Okay, so first of all, let's do some simulation of this circuit. As I've said, I don't know what is this capacitance, and I'm assuming it is like this one, 3 microfarad that we have in our unit as a beginning. And then this is a voltage source, and the resistor here is sort of decoupling this voltage source so it won't affect this capacitance. This is like a, say, power supply which is injecting a current into the unit. Put here DC just to make it more realistic that we have some DC, although it's not that important because we are dealing only with the ripple component here. And here I have a short here because I like first of all to see what is happening without the ferrite, and then we'll see how is the ferrite helping or not in this case. Now, to emulate the effect of the switcher here on this side, I've put here a current source, a pulsing current source of 1 amp, a duty cycle of 50%, and 70 kilohertz, about 70 kilohertz, as we have in our unit. So here is the situation without the ferrite bead. We see here the current pulses. We see the current of the capacitor, which are, of course, are the same because the capacitances are the same. And it is 500 milliamp peak to peak in each case, which is half of the load pulses. And here we have the ripple at the output across the 2 capacitor. And in this case, and it is 0.5 peak to peak, riding on about 14 volt. Okay, so this is without a ferrite bead. Now, with the ferrite bead, first of all, we see that we have a higher ripple, okay, at the output. That's 2 volt peak to peak. Okay, it's a higher ripple, 2 volt. And then we see here that the C1 capacitor, which is this capacitor, has sort of a sinusoidal waveform, which means that there is some oscillation here, while the second capacitor, IC2, this is this one, which is exposed to these pulses, has the combination of this resonant current and the pulses. So we see that in this case, not only that the ferrite bead doesn't help, actually it's making things worse. Now here I have the voltage across the ferrite, that is between the input and output, and you see that across this ferrite we have 3 volt peak to peak. That's a lot. So evidently we are either at resonant or at least close to resonant because we have here sort of a resonant behavior. So what is the resonant frequency of this circuit? We have a inductor of 5 microhenry, 2 capacitors of 3 microfarad, so they are in series, so we have 1.5. So we have a resonant frequency of 58 kilohertz, which is indeed very close to the 70 kilohertz, and this is why we have an appreciable resonant current. And here is the measured value. This is the voltage across the ferrite. We see that it is 2 volt peak to peak. Now this plot is courtesy of Charging Robotics, that it is involved in developing wireless charging systems. And we see that the behavior here is similar to the simulation that we ran. Obviously, we have here more noise. These are spikes due to the switching, which I'm not going into the system. The environment is very, very noisy because this is a high power system. And this part here is an auxiliary power supply, but it is, of course, affected by the surrounding units, which are of very high power. Now, to see the effect of the resonance, I'm now running a step parameter simulation in which I'm sweeping the capacitor from 0.5 microfarad to 4 microfarad. Again, with this ferrite as it is, I've added here, you see, to the 0.12, 0.08 resistance for the wire. And here is the result. This is the voltage across the ferrite. We've been here because the capacitor was assumed to be 3 microfarad, but you see that at 1.4 microfarad, we have really a resonance here, and the peak-to-peak voltage across the ferrite would have been like 10 volts. That could be actually dangerous. But when it comes to resonance, it's not just the resonant frequency which is important, but also the quality factor of the system. Okay? So here, I've added again 0.08 to the 0.12 of the DC resistance. I'm talking about low frequency, so this is what we have here. We have the 2 capacitor. I'm assuming that this is again like 3 microfarad. And then the quality factor calculated for this unit, which is the characteristic impedance over the resistance, comes up to be to 6. So indeed, we have a resonance system with quite a high Q, although we are not exactly at resonance with this 3 microfarad here, but we are pretty close, and this is why we are getting a high ripple current and voltages. Now, just to see the effect of a resistive part here, I've added here a 5 ohm resistor. This is of course not practical, because if the current here is say 1 amp, then 5 ohm would be just too much in terms of dissipation and voltage drop. Anyhow, just for the simulation, for the sake of understanding what's going on. And here is what I'm getting. So if you look now at the current of the second capacitor, this is close to the switching. You see primarily the switching because the resonant current now is much, much lower. It is 240 milliamp peak to peak, while with the actual DC resistance, it is 1.2 amp. Now, as I've said, the ferrite bead can also filter out the ripple from the source from penetrating into the load. So in this case, I've sort of switched the direction. Now I have here a ripple. This is the ripple current. I didn't put the DC now, just 0.1 amp ripple. And then we have the ferrite bead and the system that we have here, which I'm just putting here a resistive load. Now again, I'm comparing the case of no ferrite with this short and then without the short with the ferrite to see what is the effect of the ferrite bead. And here is what I see. Now without the ferrite bead, and this is the output ripple, we see here a peak of about 50 or 55 millivolts, while with the bead, we see here a larger ripple as a matter of fact. So again, for this direction from the source to the system, the bead is also not doing any job. The bead is actually harmful. Again, if I'm sweeping the capacitor, now we've been here at 3 microfarad, and this is what we got. But if the capacitance would have been smaller, the resonant frequency would have been close to the 70 kilohertz, and then we'll have a much larger ripple. So what are the conclusions of this short presentation? Well, we see that ferrite beads in power electronics are actually a double-edged sword. That is, on the one hand, you would think that they can help in some frequency range, but there is a danger that if the switching frequency or the harmonics of the signals that you have in the system are close to the resonant frequency, then of course you'll be in big trouble. So this is something to watch. I'm not saying that you cannot use ferrite, but you have to be extremely careful so that in your particular case you're outside the resonance. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.